The principle of mathematical induction is a very powerful tool for proving theorems because it allows us to prove infinitely many statements in one swell swoop. Every proof has finite length, so you cannot hope to prove infinitely many statements by just writing down all of those proofs at once. For each case separately, this technique tells you how you can economize and get around this limitation. Let P1, P2, P3, etc. be a sequence of mathematical statements. So not a sequence of numbers or functions, but a sequence of mathematical statements. Suppose, first of all, that P1 is true. And secondly, suppose that each statement in the list implies the next one. In other words, whenever Pn is true, then Pn plus 1 is also true. Then, all the statements in the list are true. We have here a kind of chain reaction like what is seen in an infinite sequence of dominoes stacked in a row. We assume each domino is close enough to the next one to knock it over, which is our second assumption here. All we need to start the chain reaction is to knock over the first domino, and that was our first assumption. So P1 is true, which implies P2, which implies P3, which then implies P4, and so on, all the way down the line. But unlike a physical sequence of dominoes, which take longer and longer to get more and more dominoes falling over without ever finishing off, here the entire sequence is knocked over without having to worry about waiting. The first condition is called the base case, or the initial case. The second condition is called the inductive step. To prove the inductive step, we really need to prove an implication, namely that Pn implies Pn plus 1. In this step, we show, conditional on the assumption of Pn, that we get Pn plus 1 as a consequence of Pn. In this case, we refer to Pn as the inductive hypothesis. Now, a subtle point in our previous video is the fact that every integer is either even or odd. This fact, which you may have taken for granted, requires proof by induction. We need to first define our terms. An even integer is one which is divisible by 2. In other words, is an integer of the form 2 times some integer. An odd integer is an integer that is one more than an even integer. In other words, it is an integer of the form 2k plus 1 for some integer k. The result we require is that this gives us a partition of the integers into 2 parts, the evens and the odds. The assertion here, which must be proved, is that every integer is either even or odd and never both. Let's talk about the proof of this statement, at least part of this statement, for which we can use mathematical induction. I will show you that every positive integer is either even or odd. It's probably the harder part of the previous assertion. You still have to prove the other part, that it can't be both, even and odd, but I won't bother with that here. For each positive integer n, I let Pn be the statement that n is either even or odd. Note that Pn is not a number, it is a statement. The initial case is not hard to check. It's the statement P1, which says that 1 is either even or odd. Well, 1 is odd, which we see from the definition, so that shows the first requirement being satisfied. Now we have to check the inductive step. Let n be any positive integer. We need to show that Pn implies Pn plus 1. In order to do this, we consider our 2 cases. Our assumption here, the inductive hypothesis, is that n is either even or odd. Well, in the first case, n being even means that n is 2k for some integer k, but then n plus 1 is 2k plus 1, which is odd by definition. So we conclude Pn plus 1 in this case. In the other case, n being odd, then n is 2k plus 1 for some integer k. And in this case, n plus 1 is twice an integer, 2 times k plus 1, which is even. The point is that in both cases, Pn plus 1 follows from Pn. So we've now satisfied the inductive step. Putting that together with our previous step, this says that our theorem follows by induction. And by the way, if every positive integer is even or odd, you quickly find that every integer is either even or odd. And then it's easy enough to see by another argument that an integer cannot be both. It's either even or odd with the exclusive or. I'll leave that as an exercise. And by the way, you don't need induction to complete this exercise. The formalism that I've described in my first slide on the structure of an inductive proof is the training wheels for doing induction. A more typical proof by induction is more organic than this, so let's look at some examples. In this example, I want to prove for every non-negative integer n, the sum 1 plus a half plus a quarter plus plus 1 over 2 to the n is less than 2. Now on the left side, we have a finite geometric series in which each term is half of the previous term. So knowing enough about geometric series, you can altogether avoid induction to prove this. Nevertheless, I am going to use induction for the sake of having an instructive example of another proof by induction. Notice the base case here is for n equals 0 rather than n equals 1. This is no substantive departure from the generic setup earlier. It just means that we are re-indexing the cases by shifting the value of n. In the base case, we just have one term on the left, which is the number 1. That's less than 2, so the conclusion holds as required. Moving on to the inductive step, we assume the inequality holds for a particular value of n greater than or equal to 0. We want to show the inequality also holds for n plus 1. For someone with just a tiny bit of experience with induction, the temptation would be possibly to just try to add one more term to both sides, which would be the next missing term, 1 over 2 to the n plus 1. But right away, you'll see that that cannot possibly lead us where we want to go. It wouldn't give a strong enough inequality. Instead, what you can do, however, divide both sides by 2 to get a half plus a quarter plus plus 1 over 2 to the n plus 1 being less than 1. Now from here, it's easy to just add 1 to both sides, and that gives us exactly the inequality we need. So we've just proved the inductive step. Whenever the proposed inequality holds for n, it also holds for n plus 1. So the statement holds for all n greater than or equal to 0 by induction. Here is another statement made in an earlier video for which we can now offer a proof by induction. Once again, induction is not the only method to prove this, but it does give us an instructive example of an inductive proof. So let n be a non-negative integer. Then a set with n elements has 2 to the n subsets, and that's what we're trying to prove. We start with the base case in which n is 0. So in this case, S has 0 elements. Well, that can only mean the empty set. There's only one subset in this case, the empty set itself. So you get one subset, 2 to the 0 is 1. As predicted by the formula, we have the right number of subsets. That takes care of the base case. Now consider the inductive step. We have a set S, let's say with n plus 1 elements. We can partition our set S with n plus 1 elements into a subset A, having n elements, disjoint union, a singleton set with one element B. So the set A has n elements. That means by the inductive hypothesis, it has exactly 2 to the n subsets. What does a subset X of S look like? If we intersect X with A, we get a subset X prime of A, and then the original subset of S, X is either X prime or X prime union the singleton set B. Each subset of A gives rise to exactly two subsets of S in this way. And this is all the subsets of S. So the number of subsets of S is exactly double the number of subsets of A. So that's 2 times 2 to the n, which equals 2 to the n plus 1, exactly as predicted by the formula. So we're done. Now there is a stronger form of induction, which is sometimes called complete induction. Once again, we have an infinite sequence of statements we want to prove. In order to do so, it suffices to show that, first of all, the first statement in the list is true, and whenever the first n statements in the list are true, then collectively they imply the next statement, the n plus first statement. In analogy with the dominoes, we first push over the first domino, which knocks over the second, then the first 2 dominoes together knock over the third, then the first 3 dominoes together knock over the fourth, and so on all down the line. As an example of how this form of induction works, we prove that every integer n greater than or equal to 2 is a product of primes. Here we are not proving the bigger result that factorization is unique. That takes more tools from algebra. Here we're just showing that n can be expressed as a product of primes, possibly one factor, of course. That's when n is prime, you only have one factor. The base case is n equals 2. That's already prime. In this case, there's just one prime factor, so that takes care of the base case. Now for the inductive step, suppose all the integers in the range from 2 up to n minus 1 have prime factorizations. Now we want to show that n itself also has a prime factorization. There are 2 cases. If n is prime, we're done. Otherwise, n not prime means n would factor as a times b, where both factors are in the range from 2 up to n minus 1. So by the inductive hypothesis, both a and b have prime factorizations. And then since n is a times b, that gives us a way of writing n itself as a product of primes. This proves the result. You can see here that the inductive step succeeds not by invoking the inductive hypothesis for n minus 1, but by invoking the inductive hypothesis for 2 numbers in the range from 2 up to n minus 1. This is fairly typical of how complete induction goes. The full power of the inductive hypothesis is there when needed, when you want to call upon it, but you don't usually need every known fact at every step of the proof. A very important reformulation of the principle of induction is something called the least number principle. This says that every non-empty subset of the natural numbers has least element. Note the requirement that S be non-empty. Of course, if S is empty, it wouldn't have any elements, so it obviously wouldn't have a least element. Also note that this only gives a least element. In general, there's no greatest element. This property is really equivalent to induction. Any proof by induction can be reworded as a proof using the least number principle. And conversely, any proof by the least number principle can be rewritten as a proof by induction. The statement of the least number principle itself can be proved using induction. Or the other way around, if you assume the least number principle, you can use that to show that induction works. I won't go through the details of what I just said. Instead, let's settle for an example of how to use this principle. We just proved by induction that every integer n greater than or equal to 2 is a product of primes. Let me rewrite this proof, not using induction, but using in its place the least number principle. Other than that difference in the organization of the proof, the details of the proof are pretty much identical, as you'll see. Here we take S to be the set of all integers n greater than or equal to 2, which cannot be factored into prime factors. The theorem we're trying to prove is that this set is empty. So let's prove that by contradiction. Suppose it's not empty, and look for a contradiction. Our assumption S is non-empty. It's a non-empty subset of the natural numbers. So by the least number principle, it must have a least element n. Evidently, this element n is not prime, since it's an S. So that means it factors as a times b for some integers a and b in the range 2 up to n minus 1. Since n is the smallest element of S, with a and b being smaller than n, that means a and b cannot themselves be in S. By definition, that means A has a prime factorization, and so does B. But remember that n is A times B, so that gives a prime factorization for n, contradicting the fact that n is in S. That's the contradiction we need. Shows that S must have, in fact, been empty. It's exactly what we set out to prove. Now, there's a name for this distinctive property of the natural numbers that we're using throughout. It's well-ordering. The non-negative integers are well-ordered, meaning that every non-empty subset of the natural numbers, or the non-negative integers, either way, has least element. We do require transitivity and what I referred to as the trichotomy property, but every order relation that I mention will have those two properties anyway. So this is an important property precisely because it is what allows us to do induction. And by the way, also recursion. Let's look for other instances of this. The integers are not well ordered. It does not even have a least element. The rational numbers also are not well ordered. There's no least element. So I guess the real numbers is not well ordered because it doesn't have a least element. And the positive reals, that also is not well ordered. Same reason. Now this interval, 0 to infinity including 0, the non-negative real numbers, has a least element. However, it's not well ordered because the positive reals is a non-empty subset of this set with no least element. Recall the definition. To be well ordered, it's required not only that your set have a least element, but that every non-empty subset also have a least element. So we are still looking for more examples of well ordering, and so far we're coming up pretty short. But this is a good one. A subset of the integers is well ordered if and only if it is bounded below. It's not hard to prove. I'll leave the proof as an exercise. Use this example of well ordering from time to time. It means you can do induction on any set of integers which is bounded below. Actually, we've used this example already in ways that I didn't explicitly point out. So for example, the exponents of x in a Laurent series that we used were from a set of integers which was bounded below. This was exactly the property that we needed to perform arithmetic operations by going through the terms recursively. Recursion and induction are almost the same thing. We talk about proving something inductively. We talk about defining something recursively, or constructing a sequence recursively. In each of these cases, the domino effect requires that our cases be indexed in a well-ordered way. There are more examples of well-ordered sets, including lots of examples that are subsets of the reals, but that's too much of a detour from where we're going now. I will mention, however, by the way, that the empty set is well-ordered. Hopefully you can see why. Every non-empty subset of the empty set has a least element. For the same reason that every non-empty subset of the empty set has 7 elements. It's just vacuously true. It holds in a vacuous sense. There is no non-empty subset of the empty set. However, as examples go, the empty set isn't actually a new example. It is an example that comes from the last line on our slide. You take a subset which is empty, is bounded below, And again, you can convince yourself of that and see it, therefore it must be well ordered. The fact that the real numbers is not well ordered is why we can't really prove statements about the reals by induction in the same way that we can for statements about the natural numbers. However, much of our course is about sequences rather than functions of a real variable. So there, well ordering plays an important role in proofs by induction. Also being able to define sequences recursively. Now, I need to correct a white lie that appears on this slide. Each example appearing on this slide comes from an ordered ring or an ordered field, and I'm only considering the usual order relation. However, it is possible to replace that order relation with a new one. A new order relation found in this way will probably not play well with the algebraic relations, but maybe it has something else going for it, like being a well ordering. Now, using the axiom of choice, it is possible to find a well ordering for any set, even for the real numbers. And then you can actually prove things that way by induction on the real numbers. One last example of a result proved by the methods of this video. This proof can be expressed either in the language of induction or using the equivalent language of well ordering. On the previous video, we used the fact that every rational number has a reduced expression. Actually, at least you need to know this much, that you can cancel twos in a fraction. So you can get a form for every fraction where numerator and denominator are not both even. So I'll just prove that special case, although the general case is not much harder. So every rational number has a reduced expression where numerator and denominator are not both even. For the proof, we let x be a rational number, let S be the set of all positive integers n, such that n times x is an integer. This is a non-empty subset of the positive integers. Why non-empty? Well, because x is rational, it can be written as a over b for some integers a and b, with b positive, so b times x is a, which is an integer. So that shows you've got an element b, which is an s. So s at least is non-empty. That's a start. So s being a non-empty subset of the positive integers, it must have a least element. I'll call that least element s. By definition of capital S, little s times x is an integer, which I'll call r. Of course, little s is non-zero, so you can divide and solve for x is r over s. All that's left is to make sure that r and s are not both even. Well, if they were both even, then r would be 2r prime, and s would equal 2s prime for some integers r prime and s prime, with s prime positive. But then you could cancel the 2's and get r prime equals s prime x, which is again an integer. So then s prime would be in capital S. And this would violate little s being the least element of capital S. There's your contradiction. So with that, we are done.